Okay, let's begin lecture 2, where we move into sensitivity, talking about, we're going to talk about specific sensitivity, the sort of economic sensitivity that really comes from thinking about what would happen if small changes happen in the problem. So economic analysis is in large part about sensitivity. So it's never the case that we find the solution to some economics problem and say, there it is, that's what you do, that's what everyone should do. It is always the case that you think about, here's the demand curve. Well, how responsive or how sensitive is everyone on this demand curve? And so that's what we're doing in these problems. We're going to generate a solution, and one of the things we could do is is produce little scenarios to see how sensitive the solution is. It turns out there's automatically one of the sort of real valuable pieces of a linear programming solution is the actual sensitivity report. It just takes some time to understand how to use it, and so we're going to go through all of that here, and in the rest of the time that we look at solutions, we'll be focused on that. So actually the example problem I'm going to work on is started back in chapter 2. So in module 2 you were asked to read chapter 2 of the Anderson et al. Book. So if you want, you can go back there, but I've pulled out all the relative pieces from the example problem and put them in the slides here so that we can set it all up. And so here we go. The Par Inc. problem. It's a golf bag problem. They have two types of golf bags they can make. They have different returns or profit margins for each of the golf bags, and then they each use resources in the firm, limiting resources in the firm at different rates. So the constraints are work time by department. The work rates are sort of accounting information using past production data. The profit contributions are return above variable costs, not the costs that are attached to our constraints. So each type is available, and that's where we start from. So we're going to be able to build an objective out of that, and here are the sort of production requirements or the technical information. So for the two types of bag, a standard bag versus deluxe bag, you're going to use 7/10 of an hour on the cutting and dyeing, 1/2 of an hour out of the sewing availability. And you see the deluxe bag here is using more of these two resources and more of this, but less of this constraint. Okay, and so these rates would let you know how the trade-off is going to occur, right? So essentially it looks like standard bags require a little bit less of a resource draw on the firm, so in some sense they're less costly, but for the deluxe bag it should be generating more returns, so it may be possible that drives up returns. The feasibility is going to be determined by those constraints, so the number of hours must be less for sewing time, must be less than or equal to the number of hours. So we're familiar with all these constraints. They give the limit or the outer boundary that will determine feasible production. We assume the coefficients are fixed, and we assume the right hand side values are fixed. So there's no reallocation of surplus hours. If something doesn't get used on the right hand side, it is gone, or it is not of use to us. We don't get to charge it back or sell it at the end without explicitly putting that in. Yeah, there's no sort of shifting things around. Now, obviously, in the real world, I've worked in a factory, and it was very common if packing or some other unit was behind that somewhere else in the production could get pulled off and asked to go work in packing, and that obviously is in day-to-day management. But if you're thinking about a planning model and trying to value things and really come up with economic information about how sort of the normal operation is set up, you don't want to build in all that sort of flexibility, because what you really want to know is, what is the value of expanding capacity in the packing department or storage, right? I mean, inventory space. You want to know what those values are under sort of normal conditions, not because some supervisor said, okay, our shift has to get these orders out, and it looks like we've already got things, built up on your line, and Keeney, you need to go help them in packing tonight. And so while one is more real, the real economics, the real structure of the firm is really less about those idiosyncratic decisions that get made on the fly. The problem formulation, so if we went through and did the exact, I think still in chapter 2, here, just to represent all the things we've been doing, here's the declaration of variables, S for standard, D for deluxe. The total profit objective would be 10S plus 9D, and we're going to maximize that. And here are the 5 constraints. So the hours of cutting and dyeing must be less than the time available. Hours used, less than the time available. And so here's an inequality constraint for each of the 4 material or production lines, all less than or equal to constraints. And then we have our non-negativity constraints as well. So the 2 activities only make sense if they're 0 or larger. And then we can get a full picture of the feasibility for this production plan, and I want to do this and get the solution in the graphical context, just so that we can think about sensitivity more clearly. So the feasible region here is defined by all the constraints where they intersect, and you can see that there's a constraint out here, the sewing constraint, that lives outside of the feasible region. It doesn't touch anything else in an interesting spot, so that's always going to be in surplus. The boundary is formed by finishing, cutting and dyeing, I think it was called, and then something in packing here, inspection and packing. And so you have the region determined by that constraint, the region sort of dominated by that one, and the region here. And so we've learned at this point that the frontier points, the points for a maximization problem, that sort of, as you push away in this direction from the origin, the 0, 0 point here, it's in general we're going to push away from this. And since we don't have any, these are what we call sort of free disposal, any resource you don't use doesn't impose a cost on you, but it also doesn't generate you any return. So this free disposal condition says, why would you ever produce interior to this feasible region? Sure, it doesn't cost you anything, but there are returns that could be generated by moving out and using those extra resources. And so the boundary out here is always efficient in a resource use context. That's sort of the technical efficiency. I think we've already talked about in this class a little bit. Technically efficient because you're using as much resources as you can. You're getting to the boundary. And so that's, again, sort of in that most limiting resource context. The allocative efficiency, or the sort of profit or economic efficiency, would be measured by finding not just that you produce on the boundary, but you find the boundary point that produces the best return, right? And so whatever you consider to be returns, however you measure it in the objective, find the boundary point, the corner point on the boundary that is best. And so here are a set of profit lines for this problem. So it is the case that S is worth 10, D is worth 9 in terms of the profit per unit, the returns above variable cost. And so these are the combinations that earn $1,800 in total profit. These combinations, $3,600. So when it says 10S plus 9D is equal to $3,600, that's a level curve or a slice of the profit equation. So, and it tells you all the combinations between S and D that give you that amount, $5,400. And you can see what's going on here is you could draw a perpendicular line through these parallel profit lines. And this line here is interesting because it represents the exact direction of increase. So you can imagine these lines, if they were steeper, then the arrow drawn perpendicular from the origin through them would look kind of like this, and it would try to tell you, it would give you much more direction about which constraint you're going to hit or which corner point you're going to hit. But this pattern of increase is something we can follow, and of course if we kept moving it out, I think you can notice that this is the corner that's going to, this space right here is going to survive the longest, and eventually you'll get down to a point where you draw a new profit line here, like this, out here. It's only touching at one point, and that one point is this corner. So you found the limits of feasibility with the profit choice that's farthest out, right here. And so that maximum profit line, the combinations of 7,668 earnings, this corner right here is the only one that is feasible. This combination is the only one that earns that much, and every other feasible combination earns less, because any profit line you draw on this side is lower than 7668. Okay, so solving this thing, you can do it graphically the way we've just kind of drawn it out. It must occur at one of the corners, so another way you might solve this would be just to examine this corner versus this corner versus this corner versus this corner and compare them all, and that would lead you to this corner being the solution. You could also say, well, I know the slope of this profit lines that I'm drawing. Remember, they're all parallel. These are all parallel, so the governing factor, the critical factor here is what is the slope of those profit lines. Well, since you know the slope, if you found that slope and you know the slope of these constraints, once you know which constraints form this boundary, then it must be the case that the slope is somewhere in between the slope of this piece of the boundary and this piece of the boundary. Okay, so this must be something that's slightly steeper, which would be I suppose that would be a more negative. Right? These are all downward sloping, so it would be larger in absolute value slope, but it would be more negative, and this would be slightly smaller in absolute value or slightly closer to zero. And so the slope of the objective is going to sit in between those. Why is that important? Well, because you could shift the rate of return for standard bags from something slightly less than 10, and this would tilt the line just a little bit in this direction. It would give it a small tilt, but not enough to move off of that corner. And so part of our sensitivity work is actually going to be thinking about how much can the per unit profits for standard versus deluxe change without causing us to jump from this corner to this corner. And so that's really the case of sensitivity. We find our best plan, it's at this corner, right? And if we wanted to do everything here, we would say this constraint is binding, this constraint is binding, this is the level of production for standard, this over here is the level of production for deluxe, and this is how much it earns. That's our full readout on a solution. And then you move to the sensitivity and say, how much can things change? How sensitive is this? Well, what are the range of profit margins that keep us on that corner? And it turns out if you exceed those and go to something like 5S plus 9D, then you jump from this corner up to this corner. Obviously the objective is now lower because one of the things we were producing went down in price, and here's a new parallel line that sits interior. So if that return for standard bags falls by 5 to 5 per unit, the solution changes, and that's something that we can predict by the range. Okay, so you have a spreadsheet. I've got what I'm going to do is, since this is a lecture, I'm going to talk through screenshots from the spreadsheet result, but you can open that spreadsheet and look at it, the solution for this as well. It also has the answer and sensitivity reports, so something we haven't looked at yet, so I'm going to talk through those here, but they're the solution for this problem. Okay, so if you solve this, this is our standard LP setup. We have some objective coefficients up here, the activity levels, and the profit measure. And then if you look down here, so you see the plan, earn 76.68, 540 is the standard production amount, 252 on the deluxe production amount. And then for the constraints, we have the cutting and drying is, maybe that's supposed to be dyeing, I'm not sure. Anyway, that one's binding, and then the finishing constraint is binding. The other two are not, they're slack. Okay, so when we talk about the economics of this problem, these are going to be the more interesting ones to talk through. Okay, so the first thing when you run Excel, and you can of course rerun solver there if you want for this model, and what it'll do is it'll show you at the end, would you like the answer report or the sensitivity report, either one of those. And the answer report looks like this. So it opens up in a new spreadsheet, and you can look in the spreadsheet there and see this. And what it does is it gives us the three components of an LP solution. So the activity level of 76, or sorry, the profit level. It says activity level here because of the way I labeled the spreadsheet, but you can make it say profit. The profit or the objective value is here, right up here, the objective cell, 76. The activity level is reported here, and then it gives you the status on the constraints. So the actual recorded value in the left-hand side, and then the status, right? So it's telling you binding versus not binding, and then the ones that are slack, that are not binding, it tells you how much slack there is. Something that's, of course, a little bit useful here maybe if you're going to do some scenarios is if you start from a different value, if you take this solution to be the new starting point and solve a new model, then the original values shift, these final values will shift over here, and you can do direct comparison of plan A versus plan B. I don't find it that useful. And I think if you keep following through this course, you'll see that maybe you don't agree with me, but at least you'll understand how I think about it and why I would think that's not too useful. The second part, and the part we're going to spend the rest of our time here on, is the sensitivity report. So the other thing you can click there, I think there's probably also some kind of limits report or something, but we're not going to use that. The sensitivity report is something we can open, and it gives, again, another report inside the spread as its own new worksheet in the spreadsheet workbook. And it reports all these different pieces of sensitivity information in tables. And so this is what the sensitivity report looks like for the model we just solved, or that I've solved for you and provided. And the first part I've yellowed out here has some components up here in the variable cell, so these are the activity levels, and it has some components down here in the constraints. And it's really what we would call historically, or it's possible in some of the readings you might have seen, dual, D-U-A-L. There's a dual side problem for every linear programming objective. You could write a different mathematical problem that solves for the sort of internal equilibrium values or prices of the firm. And so that's what these are. And so they're automatically solved for in this linear programming problem in this solution algorithm in Excel, and we call them shadow values or shadow prices. Okay, and so each activity up here gets a shadow price attached to it, and it's called reduced cost. Okay, and so you see here I've written a paragraph because I want you to have this as a reference. So these are reduced cost. Think by the label, but it's best probably to think of them as objective penalties. So by penalty, we mean if a number shows up here, it's a penalty. It will go against the direction of the objective. So in this case, if we had a reduced cost value there, it would be negative. And what it would be telling us is that the objective, the profit measure, goes down. Okay, and so these are both zeros, so it's not the best. We'll see a situation in a later part of this module where these are not all zeros, so you can actually understand them a little better. But what they really are these sort of shadow prices on the non-negativity constraints. So essentially, if we had a third activity down here and it said produce garbage bags, and nobody wanted to buy garbage bags, but for some reason, instead of a non-negativity constraint of 0, we decided that we are mandated to produce one garbage bag. That would show up as a final value of 1, and it would have a reduced cost here. It would show up here as a final value of 0 because of the non-negativity constraint. And then the reduced cost would tell us if for some reason someone makes us produce one garbage bag and use up some resources from the firm, how much our profit's going to suffer. And so that's why I call it an objective penalty. It would show up there with that third activity and tell us how much things are going to be worse off. So we'll come back to that one in a little bit. I don't think it shows up in your quiz or anything until we actually get some positive values. But it's a shadow price just like these are. So it's on the activities, but it's on the non-negativity constraint of the activities. Down here we have our actual constraints, and you've already seen this a little bit. So imagine a scenario where you were interested in knowing what it would be like to have just an extra unit of capacity on the cutting and drying floor, right, or in that section of the firm. So what you would do is resolve this model, and instead of the constraint right hand side being 630, you would set it to 631. And you would solve the model, and you would see how much profits went up, and you would measure that. That is exactly what this shadow price column is doing right here. It is answering for you the question, how much value is there in getting one additional unit to the right hand side here? So increase this by 1, you improve profits by 4.375. Increase this by 1 to 601, you do nothing to profits because this was already a slack constraint. Increase this by 1 to 709, this shadow price tells you how much the value in the problem goes up, how much the returns go up. And so easily some of the most valuable pieces of these solutions is in the sensitivity report. And of course, a huge boon to linear programming as a technique is this automatic calculation of these shadow values. A way to go in and price every constraint that limits your solution. You go in and you get a price that tells you what it's like, what it would be like if that constraint was relaxed just a little bit. As an alternative, you could think about it being also the return or the value to the firm of the last unit, right? So the last unit and next unit are both marginal in the classic sense when you're thinking about one full unit. We're not thinking about a calculus, sort of a infinitesimally small change. The second part of the sensitivity report has to do with the ranges. Okay, so if the first part was about these columns, sorry, that's supposed to be yellow there. If it was about these pieces that are yellowed in here, the second part, the ranges, are about all of the stuff that's remaining. And what these are is, if we go back and look at, sorry, I'm just zipping. Remember, we said if this line starts to tilt because the return for standard bag starts falling, so this line starts to tilt this way, well, what these ranges are doing in this sensitivity report are telling us how much tilt can you get, how much can these things fall or go up, right? This objective coefficient, how much can it fall or how much can it go up before this solution changes? Okay, so allowable increase here says 10. If you add 3.5 or less to that as the new measure of profit per unit, then that's fine, and this solution here won't change. 540 and 252 remain the best plan. Allowable decrease, if you just subtract 3.7 from 10, this still stays the solution. If you go beyond 3.7 and reduce it down to 5 like we did in that graph, then the new plan, this plan is no longer valid. It's no longer the best plan, and these things will start to change. Down here for the constraints, we have something just a little different. So if these allowable increases and decreases say, how much can the objective coefficient change before we get an adjustment to these variable outcomes? Well, down here, what it's telling us is, how much can the right-hand side of this problem, of this particular constraint, go up or go down before the shadow price changes? Okay, so these are variable results. These are solution pieces of the problem. And even though we don't calculate them like they are variables, these are also solution pieces. These are the dual variables or the shadow variables of this problem. And so that is telling us that you can add 50 units to this constraint on the right hand side, and you know that each unit is worth $4.38 approximately. If you add 60 units to the right hand side of this, you don't know what the value per unit is, right? It's going to change. And so this is just telling us how many units additional can you put on the right hand side here and know that the marginal return, or the per unit return or gain to the firm, is 4.375. Of course, when you have these constraints that aren't binding, you end up with an infinity symbol here. This is what 1e to the 30 means. That means you can increase the right hand side here forever. It's still going to be shadow price of 0, and then the allowable decrease is just the slack, right? So if this thing goes down by the amount of the slack, then it starts to bind. If it goes down by more than the slack, then we are going to change the shadow prices, because suddenly we're going to have a new binding constraint on our hands. Okay, so if you wanted to go through and do this in your spreadsheet and see all these things pop up, here's how it would look. So a reduction of the coefficient on the standard bag that is within the allowable decrease. Remember, the allowable decrease on this is 3.5, so lowering the return per unit for standard bags by 3 shouldn't change the solution, the plan. So 10 down to 7, I resolved it, and I got these, which are the same exact activities levels. The one thing that does change is the profit, because we changed the profit per unit. It's still the highest profit attached to this plan. It's just it's a less valuable plan because the market's no longer giving us the same return for those. The same constraints will be binding, right? So if these activity levels stay the same, then these same constraints will bind that did before. Now, if we go beyond the allowable decrease, we shake up the problem quite a bit. So 5 is bigger than that allowable decrease, so we go down from 10 to 5. We end up with a new production plan, a new objective variable, which we changed last time, and then of course what's really interesting is we're going to shift from one constraint being to the so this constraint is going to remain binding, and this will be the new binding constraint. So we jump from one corner of the problem to another corner of the problem, and so that means that we are going to have instead of the 2 constraints here that were crossed at the old corner, we're going to need the intersection at the new corners between cutting and drying and inspection and packing. And then on the constraint right hand sides, you can see here what I've done is I've increased the right hand side of this constraint by 50. Remember, I already gave you that as an example. So if you increase that right hand side from 630 to 680, the shadow price stays the same, and indeed we see that it does. And in fact, the allowable increase now is quite small. It's down to 2.36. If we go above the allowable increase, so we increase the right hand side of cutting and drying by 70, that's bigger than the allowable increase was on our starting problem. What we end up with is the right hand side of the constraint that's 700, and then the final value on the constraint is only 682, so it's not binding anymore. There's now slack, and the shadow price of course has to fall. And since it's not binding, it only has one thing to fall to, and that's 0. Okay, so if you reverse this and start tightening the constraint down, and you go down below 17.63, then you would start to move the problem back and create this new corner of the solution that had the old shadow price back. Okay, just some summary. We're going to keep working on this, but just talking through everything, and we're going to get repetition on this. So if you end this lecture thinking I don't quite understand it, well, there's going to be some quiz questions that direct you back into this on things to look at to help you remind, but we're going to get a lot of practice with these as we move through the end of this module. Sensitivity is an important source of sort of economic and managerial information. Mathematically, that dual or shadow nature of the problem gives us a lot of internal valuations, on things that we wouldn't have access to, or we would only have just guesses at. Those shadow values on activities are just, again, Excel calls them reduced cost. I always thought of them as objective penalties. But remember, as long as a variable shows up as a positive value, something bigger than 0, it always has a 0 objective penalty. If a variable is optimally set to exactly 0, then it will have that objective penalty, and that penalty says you shouldn't be doing this. The optimal plan includes this being set at 0, but if for some reason you're forced to use it, You're forced to use to make this product or to use renewable resources when in fact it's cheaper to use other things, then you're going to be penalized for it. You're going to incur extra costs from that sort of force of adopting that into the plan. Constraints: how does the right-hand shadow prices, how does the objective change on the right-hand side? So just pricing out or coming up with the profit measure that is attached to an additional resource unit. Other things worth noting, the signs on these things can change, so the penalties can be positive or negative. They always are a penalty though. So if you're trying to make something large, then they show up as negative as a penalty. If you're trying to make something small, a minimization, then they show up as positive. Good, bad, better, worse are always defined by the direction of optimization. So a negative impact in a cost minimization problem is something that drives costs up. So you end up with these positive numbers that are in some sense negative. And so it becomes difficult to talk about, so you always have to contextualize your discussion and try to contextualize the way I'm talking about something. If I say negative, I try to be careful. But if I say good, bad, always think about what is the context of this problem. The Excel algorithm is going to give us these ranges automatically as part of our sensitivity, which is a really cool thing because it lets us know, if economics is all about sort of elasticity and knowing about how much prices can change and how quantities will respond in adjustment, well, here it's about how much prices can change before we need to sort of sit down and resolve our problem and think about whether we're doing the best plan or not, because the best plan may be the best under a big range of values. With that, sorry, I have one final slide there, but it seems to be gone now. It is that graph where I had the arrow pointing from one to the other if you want to review it. But yeah, it's about telling us how big of a swing can you get in the slope of that objective line before you jump from one corner to the other. And then of course for the constraints, that range measure is about how big can you grow or shrink that right hand side before you change the other variables in the problem, these marginal valuations, these shadow prices. With that, we'll shut down this lecture and be sort of at the end of our sensitivity discussion that is specifically focused on structure and sensitivity, and we'll move into transportation network as our next topic.